Okay, now I will derive equations of motion based on the definitions of velocity and acceleration for the case of constant acceleration. So what's an equation of motion? An equation of motion is something that tells you what the position is at some point in time. So it's basically position as a function of time. So it's going to be a whole bunch of stuff that includes time. And then we're also going to have an equation for velocity as a function of time. So it's going to be a whole bunch of stuff that also involves time. So it tells you where the object is at any given time and how fast it's moving at any given time. So that can be a pretty useful thing for solving problems. So first we're going to derive these equations of motion. I could just give them to you and then you use them to solve problems, but it's useful to see where they come from. So first let's look at what all these expressions with delta mean. Delta x is really x final minus an x initial. Now for the sake of notation, we tend to write x final as just x, and then x initial as x0. Initial x, and then this is final x. So that's just a standard way of writing it. It means the same thing. Basically your final x, we just call it x. Your initial x, we call x0. Delta v is v final minus v initial, which is, again, v is your final velocity, and your initial velocity is v0. What that means is v at the time t equals 0. Initial v at time t equals 0. And then finally we have delta t is t final minus t initial, so t final minus t initial, which is t minus t0. Now t0 that's your initial time. Your initial time is generally 0, unless you have some special problem where you don't want it to be. Just assume that this is 0. So in other words, delta t is really just t. So we needed the delta t and the delta x and the delta v so that the definitions could be general and apply to anything. We're applying it to this notation, where the delta t is really just the time from 0. So the beginning of every problem is t equals 0. And then delta v, we're just calling it v minus v0, and delta x is x minus x0. So that's just like basically just a change in notation. So let's look at this one. So if we take this, so we have acceleration equals v minus v0 over t. So let's arrange it for v. So basically we get at equals v minus v0. I'm going to add v0 to both sides and flip it all around. So v equals v0 plus at. So that's our first equation of motion. That is the velocity as a function of time. Now everything on the right side, in this case, should be something that we know. We know the initial velocity, we know the acceleration. So if you know those two things, then time is your variable. So you want to know at time t equals 1, what's the velocity? At time t equals 2, what's the velocity? So before we made a table of time and velocity, and for the case where a equals 5 meters per second squared, and we could figure out that at time t equals 1, the velocity was 5, and time t equals 2, the velocity was 10, and time t equals 3, because we know what acceleration means. An acceleration of 5 meters per second squared means that for every second you're adding 5 meters per second of velocity. So at time t equals 1, we add 5. Time t equals 2, we add another 5. Add another 5. But that's reflected in this equation. As I promised, you don't need to write a table and figure it out. It's reflected in this equation. If you're starting from rest, so v0 is 0, and then basically just take your acceleration, 5, multiply it by the time, which is whatever number you have for time, and then that will get you your final velocity. So this equation of motion is quite useful. So this is the first equation of motion that we've derived. However, in the list of equations of motion, it's really our second one. Our first one is going to be x as a function of time, and our second one is velocity as a function of time. So I'm going to put this over here as like number 2, and then we're going to fill in number 1 and number 3. So now that I've got it over here, I can erase this and look at our next equation of motion. Okay, for the next equation of motion, for position as a function of time, we're going to start with this one. If we rearrange this as delta x equals average velocity times time, so remember delta t just becomes t. So now we have, we sort of have delta x as a function of time, but we have this average velocity here. We don't always know the average velocity when you start a problem. So we need to do something with that. So let's look at another expression for average velocity. So recall that the average of two numbers is just you add them up divided by 2. Well, it works for average velocity as well. The initial velocity and the final velocity divided by 2. How does that work? If we make a velocity time graph, we see that as time goes from 0 to t, the velocity will go from v0 to v, which is v final. So the graph is going to look like this, and since we're dealing with constant acceleration, it's just going to be a straight line, constant slope. So now we can just see from the graph that the average velocity is really just the middle velocity. It's the one in between. That's the average velocity. So it's really the average number between v0 and v. So we can say that the average velocity is v0 plus v divided by 2. Just the middle number right in here. So this is average velocity. That only works in the case of constant acceleration, which is the case we're dealing with here. So now we have an expression for average velocity in terms of v0 and v, which might make this a little bit easier to deal with. So let's plug it in. So we have delta x equals all of this stuff, v0 plus v over 2 times time. Now, the next thing we need to do is get rid of this v final, because what we're looking for is an expression for the displacement, delta x, in terms of time with everything else known. Now, we don't always know what the final velocity is when we're starting a problem. So we can use this equation to substitute for v. So we get v0 plus all of this, v0 plus at, all over 2 times time. So now we see that we have delta x in terms of initial velocity, which is something we know, and the acceleration, which is something we know. So a basic problem might start with, here's the initial velocity, here's the acceleration, what is the displacement at some time t? Now that's not to say that there might be some more complicated problems where you're solving for any one of these different variables, but we want the equation of motion to reflect the case where we know some initial conditions. We know the initial velocity and the acceleration, and then the displacement will be expressed as a function of time. That's what we're after. So let's just do some algebra here. So we have v0 plus v0 is 2v0 plus at over 2 times time. We can distribute the t through there. 2v0t plus at squared all over 2. We can divide each thing by 2, and we get v0t plus at squared over 2, or 1/2 at squared. So this is actually, let me bring the delta x down here so we can see it. This is actually the answer. So this is our expression for delta x as a function of time. So this becomes the first equation of motion. Delta x equals v0t plus 1/2 at squared. So here we have delta x as a function of time, and we have v as a function of time. Now, delta x, as we said before, is x minus x0. So this equation could be written x equals x0 plus v0t plus 1/2 at squared. And you'll see it that way in many textbooks. The way I have it written on the equation sheet is like this, because we generally deal with just the delta x, like that's kind of our variable. So we'll see in some problems that you don't really need to separate out the x and the x0 for most problems. But just so you know that if you see it this way in a textbook, that's the same equation as this one. Now, to derive our third equation of motion, what this is going to be is an expression of v and delta x, but no t. So we're trying to eliminate t. So from these two equations, we can derive an expression that has all this information but no t. So the way you could do it is you can solve this for t, plug it in here, and it would be a big mess, but you get the right answer. But I'll show you a little more straightforward way to do that. But basically we have x as a function of time, velocity as a function of time. The last equation will be an expression that relates x and v directly without time in the middle. While the third equation doesn't really provide new information, it's derived from these two, it can be helpful as a separate equation to solve many problems. So let's start with this one. So multiplying both sides by t, so remember delta t becomes just t, so we have delta v equals at. So we'll start with this expression, and our goal is to get rid of t. So how do we get rid of t? Well, we can use the t here in this expression. We can solve this expression for t and plug it in there, and then that'll get rid of t. So this one is t equals delta x over v average. So if I plug that in for t, it's going to look like this. A and t is delta x over v average. Now, we don't really like to have v average in our equations because, again, that's something that's not usually known in advance of the problem, and it's also not a very useful quantity for most problems. So remember, we had v is v0 plus v over 2. And we can substitute that in for the average velocity. So we get delta v equals a delta x over this whole thing. So v0 plus v over 2. So basically, the 2 comes up top. So we end up with 2a delta x over v0 plus v. All right, the delta v, if you recall, is v minus v0. So this is v minus v0 equals 2a delta x over, I'm going to flip this, instead of v0 plus v, I'm going to write it as v plus v0. Just to make it a little bit more consistent with what's over here. So we have v minus v0 equals 2a delta x over v plus v0. So now let's multiply both sides by v plus v0 to get things out of the denominator. I'm going to do a little algebra here, but v minus v0, v plus v0 equals 2a delta x. All right, so we could FOIL this all out, but if you recall that the product of two things where it's like a plus b, a minus b, what you're going to get is a squared minus b squared. So you could multiply this all out to prove it yourself, but it's commonly known that a squared minus b squared is a plus b times a minus b, and that's the same situation we have here. Okay, equals 2a delta x. So we're pretty much there. So the way it's expressed is v0 squared equals v0 squared plus 2a delta x. So this is our third equation. V squared equals v0 squared plus 2a delta x. So now we have our three equations of motion. We have x as a function of time, we have velocity as a function of time, and we have the relationship between v and delta x without time involved. So these three equations of motion, if you recall what we just went through, were derived simply from the definition of velocity and acceleration with the condition that the acceleration is constant. So there's really nothing new here. These come out of the definitions of velocity and acceleration with the condition that acceleration is constant. So eventually you forget about where they came from and you just start using them. But I wanted you to see where they come from. So what's going to happen is, going forward, we're going to have examples where we use all these equations, and we'll see that when we're solving certain types of problems, some equations are useful in some situations, and one of the other equations might be more useful in a different situation. So we'll get used to how these equations are useful, and we'll develop skills for using these equations to solve problems.